In this video, we're building a fully autonomous ESP32 Scout rover from scratch. When most people hear autonomous robot, they imagine artificial intelligence, something complex, almost like a brain making decisions, but real-world robotics starts much simpler than that. It begins with a sense-decide-act loop. The robot gathers information about its environment, processes that data using a set of rules, and then acts on that as a result. There's no magic, there's no AI, just fast, consistent decision-making driven entirely by sensor input. In the last video, we added telemetry to our RC vehicle. Today we're taking that sensor data and we're going to use it to start to let the robot make its own decisions. At the center of the system is an ESP32. It's the brain of the rover. It reads all the incoming sensor data, runs the decision logic, and outputs pulse width modulation signals to two independent ESCs for left and right drive. By controlling each side separately, we get full tank-style steering, allowing for pivoting turns and precise directional correction without a steering servo. This chassis uses 6 N20 motors on a simple crawler-style frame with independent side drive, giving it stable movement and strong low-speed control. You can build this setup with any basic N20 motor frame and mounts. The structure is simple, but the control system is where the intelligence comes in. Make sure you reverse the polarity of the motors on opposite sides so they spin in the right direction. Left side motors are connected to one ESC, while right side are connected to the other. The wheels are recycled from an RC toy from a thrift store. You can attach the wheels to the motor shafts by drilling out the plastic connectors meant to go on the axle. The shaft of an N20 motor is normally thicker than the shaft of a toy axle, so you can get a snug fit by using a tiny drill bit to widen the slot. Each sensor gives the robot a different piece of the puzzle. These N20 motors include built-in encoders that generate pulses as the wheels turn. The ESP32 counts these pulses and converts them into a distance and speed based on wheel diameter. Without encoders, the robot has no idea if it's actually moving or just slipping. With them, we get odometry, a constant estimate of how far each side has traveled. If one side moves farther than the other, the robot can immediately correct for drift. This time-of-flight sensor acts as the robot's eyes for close-range distance. It fires a laser and measures reflection time to detect distance with millimeter accuracy, up to 2 meters. This is the primary optical detection system. When distance drops below a threshold, the robot immediately stops and switches to avoidance behavior. The ultrasonic sensor covers longer range, up to around 4 meters, but with lower precision. It acts as an early warning system. When it detects an object ahead, the robot begins slowing down. When the time-of-flight sensor confirms proximity, the robot fully reacts. Together, they create layered perception, similar to real autonomous systems. The compass provides a fixed reference heading, independent of wheel slip or terrain. Even if one side loses traction, the robot still knows its true orientation. This enables heading hold, keeping the robot aligned with its intended direction no matter what the wheels are doing. The GPS module streams position, speed, and altitude data into the system and the local web server. For now, we're just using it for live tracking and visualization. Later, it will enable waypoint navigation, allowing the robot to follow a sequence of GPS coordinates, and eventually a return to home feature where it can navigate back to its starting point. Since GPS only works outdoors, the system is designed to run fully without it during indoor testing. All distance sensors are mounted on a rotating servo mass. Instead of a fixed forward-facing vision, the robot can actively scan its surroundings. This is called active perception. The robot doesn't wait for obstacles to appear. It looks for them before they become a problem. The robot operates through a finite state machine, constantly switching between modes like driving, avoiding, scanning, recovering, or stopped. Every sensor input can trigger a state change, keeping behavior structured, predictable, and easy to debug, a core concept in real robotic systems. The main control loop runs continuously on the ESP32. First, all sensors are sampled, distance readings, encoder values, compass heading, GPS position. Next, the system evaluates those readings against defined thresholds and determines the current state. Then motor commands are generated and sent to the ESCs, while encoder feedback confirms whether the robot has actually moved. If drift is detected through encoders or compass data, corrections are applied in real time. And when things don't work immediately, the robot doesn't just stop. It tracks an internal frustration level. If it repeatedly fails or moves to escape a situation, it increases effort, using stronger motor output, reverser temps, or wiggle behavior to break free. The real magic happens during tuning. Adjusting stop distances, tweaking avoidance angles, and refining stuck detection turns this from a basic program into something that feels alive. This is where the robot stops feeling like code and starts feeling like behavior. We can also expand this much further. We can program features like wall detection and human tracking using a PIR sensor. Arduinos and ESP32s have limited computer processing power for more advanced robot features. For things like object recognition, we need to use a more powerful platform like a Raspberry Pi. On board, we've included a small OLED display showing real-time state and decision output, acting like a live debug monitor for the robot's thought process. Unlike ESP Now used in earlier builds for low latency control, Wi-Fi gives us much more flexibility, larger data streams, remote monitoring from any device, and the ability to integrate a live onboard camera feed so we can actually see what the robot sees in real time. We've included a local web server working over Wi-Fi that provides updates from the robot as well as a manual override joystick and emergency stop. In the future, we'll use this to manage GPS waypoints, set home locations, and even show the robot's location on a map. If you want to check out the code, the link is in the description. If you end up making your own version, feel free to share it on the Maker Creation Lab YouTube community page. Thanks for watching the video. If you want to see more builds like this, make sure to like and subscribe, and we'll see you in the next video.